Alright, first and second hour chemistry, you are in the correct place. This is your video on 14.3, which you need to watch sometime this week in preparation for Monday. 14.3 is going to summarize and finish up what we've been talking about in all of chapter 14, which is acids and bases. And what's going to really focus on is a conjugate acid and conjugate base pair. Now, what is a conjugate acid and what is a conjugate base? Well, what we have here is let's talk about this. What is a conjugate base? Well, on Tuesday, we talked about the different types of acids and bases. Bronsted-Lowry, Lewis, Arrhenius. We've talked about all of those. A conjugate base is a species that remains after a Bronsted-Lowry acid is given up a proton. Essentially, what it is it's the leftover of the acid. So if we look at this example, we have HF, hydrofluoric acid, reacting with water. We know that HF is our acid. Let's look at our two products here. What is the leftover of our acid? Well, HF was what started. Our leftover is F. HF was initially our acid. Therefore, F is going to be our conjugate base. So it's really generally acting as a flip-flop. We have HF, hydrofluoric acid, that's our acid. What's left over from the acid? F, that's our conjugate base. So that's conjugate bases. Conjugate acids work in the same way, except instead of being the leftover, a conjugate base is the leftover of an acid. A conjugate acid is the leftover of a base. So we kind of have the flip-flop here. So I'll kind of highlight the important part. We have the leftover of an acid for a conjugate base, and we have the leftover of a base for a conjugate acid. It's usually positive. So if we take a look at this example here, we have the same example. We have an acid and a base reacting together. HF is our acid, H2O is our base. Now if we look at the products again, let's look at these products. What is our leftover of our base? Well, our base is H2O. Our leftover is H3O. So therefore, H3O is our conjugate acid. It generally acts like a flip-flop. So what's that mean is if it's in the reactants as an acid, the leftover in the products is its conjugate base. And if in the reactants it's a base, its leftover in the products is a conjugate acid. So that is the flip-flop. So what we're going to continue to work on is acid-base reactions. What happens when I take an acid and I mix it with a base? Those are the things that we're going to work on. And when we talk about acid-base reactions, we have to talk about amphoteric compounds. Now, what is an amphoteric compound? It's a compound that can act as both an acid and a base. So it's a compound that can act as both an acid and a base. Now, what's the only compound we've talked about so far that has that ability? Water. Water is the best example, and for all our purposes in general introductory chemistry, water is about the only example. So amphoteric can act as an acid or a base. So when you have water, you have to figure out whether it is an acid or a base. In other terms, for the most part, though, when we talk about neutralization reactions, we're talking about the mixing of an acid and the mixing of a base. A neutralization reaction, what happens? You mix an acid and a base, they're going to neutralize one another or cancel out. Acids and bases neutralize one another. They cancel out. And when they do that, they end up forming two products, salt and water. So anytime you mix an acid and a base together, your two products are going to be salt and water. Now water obviously is H2O. Remember, from a chemical standpoint, salt is really any metal with a halogen for our purposes. So alkali metals or alkali earth metals combining with a halogen is a salt. So just not NaCl. So keep that in mind. Anytime you mix an acid and a base, you're going to get salt and water. So here's an example. I mix hydrochloric acid, a very strong acid with sodium hydroxide, a strong base, and I'm going to get NaCl plus H2O. Now, it ended up being that my salt there was NaCl, but remember that there are more salts than just NaCl. So, general rule is when you have to predict acid-base reactions, what you have happening is a double replacement reaction. So, first things first, your H and your OH combine to make H2O. Your other two elements, or ions, form to create salt. Now, a salt, if you want to make it even simpler, is a salt forms with the positive part of a base and the negative part of an acid. So the positive part of a base and the negative part of an acid. So let's practice here real quick with an example. I'm going to take phosphoric acid, H3PO4. I'm going to mix it with potassium hydroxide. And I'm going to have to predict my two products. Now, remember, anytime you have an acid and a base react, you're going to have H and OH combine to make water. Now that's H2O. I know I have 4 H's, but I am not going to just put H2O. We're going to have to come back and balance this. Next up, I have to figure out a salt. Well, the salt is going to be these other two elements, K and PO4. But I need to make sure I balance out everything. K has a charge of +1. PO4 has a charge of -3. So the compound that they would make is going to be K3PO4. Because I have to balance charges. I have to make sure all my compounds equal 0. Next up, when I'm finally done, I have to go through and balance this whole thing. Now, remember when you're balancing, you always save hydrogens and oxygens until the very end. All right, so I'm going to go 1 PO4, 1 PO4, we're good. 1 K, 3 Ks, so I'm going to put a 3 here. Now I'm going to do my H's. I have 3 H's here. I have 3 H's. I have 3 H's in H3PO4. I have 3 H's and 3 KOH, so I have 6 H's total on the top. So to make 6 H's on the bottom, I'm going to put a 3 on H2O. And I have 3 waters and 3 waters, so that is good. We are going to continue to practice and review next week acid-base reactions. But here's just an example. You have H and OH combining together to make water. And you have the positive part of a base and the negative part of an acid combining together to make salt. So again, H and OH combine to make water. The other two remaining elements make salt. And we will continue to work with that when we do acid-base reactions, or what sometimes can be called neutralization reactions. So a couple general terms, and we're going to be done here. Neutralization reactions, we talked about an acid and a base react. You can also have H3O plus and OH minus react to form water. That would be an example of neutralization. Salt, we've talked about salts in the regards to when I mix an acid and a base, I get water and a salt. A salt is an ionic compound. It's the cation of the base, the positive part of the base, and the anion or the negative part of the acid was the salt. Two terms we talked about in these slides already. And lastly, just a little brief snippet on acid rain. If you remember from the video, acid rain has the same pH as tomato juice. It's as we study pollution, we're studying really figuring out the causes of acid rain, what it does to things in the environment. And it's actually, we're starting to scale back as we figure out that the amount of pollutants we put in the air has a massive effect on acid rain and other parts of the environment. But acid rain is essentially rain that's acidic. Water, remember, is neutral. Acid rain is going to be slightly acidic. And the pollutants it mixes with Those 6 that are labeled there, you don't have to know those, but that's just a general idea of what happens. Those 6 pollutants mix together in acid rain that creates slightly acidic product. So that's kind of acid rain, and it has an effect on lakes, streams, statues, everything possible acid rain has an effect on. So there is acid-base reactions. We will talk more about this next week.